Now finally, let's take a look at the latest and most optimized trends in AI research. We'll be looking at the following 3 topics. First, let's examine the main methodologies for utilizing AI in the field of optimization. Earlier, I explained this diagram once before. To recap once again, first, research on predictive AI was necessary, and then research on generative AI became needed. So, as shown here, when you have a function y gog fx and x of gy, I mentioned that optimal design can be achieved in 2 ways. There is the traditional approach of optimal design using an optimizer, and the inverse design method using AI to generate solutions. In the case of the traditional design method, if there is a target y, you generate a new design that can satisfy that target y, then input that new design into the prediction model, and find the g in the latent space that minimizes the difference between the predicted value and the target. Then you put that g back into the generative model to find x. On the other hand, with inverse design, instead of going through this sequential process, you can simply give the target y as a condition to the generative model itself and have it generate an optimized x that matches it. Let's first look at the method using a traditional optimizer. Let's take a look at it. First of all, this is basically the process we've been designing so far. If we are to design a truck's suspension based on simulation as shown here, we need to define the problem. So we have to determine what the objective function is, what the goal is, what the design variables are, and what the constraints are. Especially when defining the design variables, we define them parametrically as shown here, fix most of the values, and then select only a few really important values as the design variables. After that, by slightly changing those few design variables, new designs are created, and then CAE analysis is performed on them. Based on the analyzed results, a meta model is built using traditional machine learning techniques. Using this meta model, gradient-based optimization is performed as shown here. This was the conventional simulation-based optimal design method. However, with the advent of deep learning, instead of parameterizing the problem as before, dimensionality reduction is performed so that feature extraction happens automatically in the reduced dimension. This way, there is no need to fix or select specific values. Then, based on these features, designs are generated in a non-parametric way, and CAE simulations are performed on those generated designs. The simulation results are then used for training, and unlike traditional methods, this allows for predicting fields, or even highly nonlinear or time series data. Building upon the foundation of that, by utilizing the power of inverse design, you can automatically generate the specific design you are looking for in real time. Or you can alternatively use reinforcement learning to make the entire process of finding such solutions significantly more streamlined and efficient. If we take another look at the classification between traditional optimal design and deep learning-based inverse design, in the case of optimal design, since it uses an optimizer, it generates a single design each time through iterative optimization. However, deep learning-based inverse design is generative, so it produces optimal solutions in real time. In the case of optimal design, there are 2 methods. One is the non-gradient-based method, and the other is the gradient-based method. Usually, the most well-known non-gradient method is GA, so you randomly generate a population and then mix only the good ones to create new candidates. As for gradient-based methods, there are approaches like SQP, which numerically calculate gradients, or you can use analytical methods that compute exact gradients mathematically, such as backpropagation. Backpropagation is also used when training deep learning models. In that case as well, a gradient-based method is being utilized. But when it comes to inverse design, you can utilize these 3 methods. You can also make use of backpropagation. When generating, you can use supervised learning or unsupervised learning. Especially if you use supervised learning for inverse design, you can generate a single solution. You generate the most optimized X for a given target Y. If you use unsupervised learning, multiple solutions are possible. You can find various X's for a single Y. In single solution, supervised learning, thank you for your attention. Inverse networks and tandem networks are commonly used. And in the case of multiple solutions, you can easily utilize conditional GANs. That's because the Y value can be included in this condition. So if you ask which method is the best, you need to consider various criteria. You need to consider things like computational cost, what the optimal accuracy is, how many dimensions your design space has, and whether the solution can converge well. After thinking about all these factors, you should choose one of these 5 methods that best suits your needs, the most efficient method. So first, the most basic approach is to create a surrogate model using machine learning or deep learning, and then perform optimization with a traditional optimizer. For example, the original optimal design method involves selecting initial points based on a meta model, deciding which optimizer to use, and then using the surrogate model to quickly perform calculations. As the solution converges, that becomes the optimal design. In this case, you can think of it as directly using a surrogate model built with deep learning as your surrogate model. In this case, the optimization was performed on the heat distribution for the heat source. Also, there are cases where optimal design is combined with generative models. So, instead of relying solely on traditional methods of parameterization, you can use a GAN to generate a wide variety of innovative new designs, thoroughly analyze those new designs, and then, based on the comprehensive analysis results, identify and select the most highly optimized design possible. And you can also use reinforcement learning. Reinforcement learning is exceptionally well suited and effective for complex sequences of serial actions, since it is inherently ideal for tasks that are carried out step by step. Rather than attempting to architect the entire system simultaneously, it is most appropriate for methods like discovering optimal spatial layouts or designing intricate structures where you carefully build up the design one element at a time. And still, the most standard method is ultimately to build a generative model, and when you create a generative model, a latent space will be formed. Within that latent feature space, you use GA or heuristic methods to find the best Z. By finding that Z, you can reconstruct the X you want. This is the most generalized optimal design using deep learning. You build a generative model, find the latent space, and then within that latent space, you find the one with the most optimized performance and reconstruct it as X. Next, let's take a look at real-time inverse design. For example, let's say we're designing a brake caliper like this. In this case, the cross-section is important. So let's call this cross-section X, which is the design, and the analysis result Y. Then the first thing you can do is build a predictive AI model. When design X is input, output Y can be predicted, but what the designer really wants is to input Y and have the system generate, in real time, an optimized X that satisfies that input Y. So X becomes a function of Y, which means creating a function Fy, the inverse function. But if you think about it simply, it might seem like you can just swap the order of X and Y and train the model that way, but it doesn't work well if you do that. That's because there are certain conditions for the existence of an inverse function. What is it? It's a one-to-one correspondence. If there is one Y for each X, then you can just train the inverse function in reverse, but if for one X, to put it another way, if there is one X for each Y, if it's a one-to-one correspondence, then the inverse function exists right away. But if there are multiple X's for a single Y, the inverse function can't go backwards. However, in the field of design, there are frequently encountered situations where entirely different designs result in the same performance. Of course, that is indeed the case in many practical scenarios. That's why you can't simply swap X and Y and train the model. So this led to the following idea. Deep learning-based inverse design is ultimately about generating the optimized X when you give Y as the target. For example, in this design, let's say we want to optimize this length. Then the most naive way, as mentioned earlier, is to consider the target Y. Think of this as the performance. When we try to directly train an inverse function like this to find the optimized X for a given target Y, it didn't work well. Right? That's because, as I mentioned earlier, it's not a one-to-one correspondence. So what method did we use? First, we build a predictive AI model. So after creating a predictive model where X goes in and Y comes out, we freeze that model. In other words, we fix it. Next, we train a model where Y goes in and X comes out like this on the back end. y goes in and x is generated. If this x is then fed back into the pre-trained predictive model I made earlier and the original target y comes out, then as you train it like an autoencoder eventually, if you just separate out this part, you end up with a generative model that can produce x from y. This method also works really well. Finally, but however, because it's supervised learning, a specific y will only generate a single x, so you can't produce diverse solutions for the same y. That's why what I considered next was semi-supervised learning. In the case of semi-supervised learning, you can use CGEN to apply a very simple concept. Now Z exists. There is a latent space, and instead of C, you input the Y performance. By generating in this way, you end up with various designs for each C. Now, even for the same Y, multiple designs can exist. Now, to explain the supervised learning method once again with a real example. Let's say you want to design the cross-section of a brake caliper, as mentioned earlier. If that cross-section is parameterized, it can be represented as an X with 13,000 dimensions, like this. That X is input, and you first create predictive models that can predict the Y you want. So after doing this with supervised learning, these models are called forward networks, and we attach the forward network at the front. With the forward network at the front, when you input X, you get Y. Then at the back, you attach this inverse network, which generates X when you input Y. So if you provide the target performance values, Y1 to Y4, X is generated, and then that X is again. This data goes directly into the sophisticated prediction model architecture so that the variable Y is reproduced with identical precision and accuracy, and the model is trained extensively in this specific way. Pakar. Once that entire process is successfully done, you can safely remove this part and use only this section to achieve the exact design you want. Naturally, from a technical optimization perspective, after all the training is complete, you only need to perform the forwarding process, so the overall optimization time is significantly and drastically reduced to a fraction of its original time. In fact, what used to take about a full month of computation is now evaluated to take just 1 single minute.